Welcome to the Data Vault, a visual guide to database integrity constraints. This video explores the architectural principles for creating accurate, consistent, and reliable systems. Without strict rules, simultaneously accessed databases suffer from invalid data, duplicates, and missing references, leading to the fragile database state. Integrity constraints are the structures that prevent data corruption and enforce business logic, leading to an ironclad database. An integrity constraint is a condition or restriction imposed on database tables. These constraints maintain data accuracy, enforce business rules, and ensure relational consistency by keeping linked tables synchronized. Integrity constraints fall into two main categories: structural constraints and value validation constraints. Structural constraints include key, entity, and referential, forming the core foundation. Value validation constraints include domain, check, not null, unique, and default, which enforce granular business logic. The key constraint enforces row uniqueness, ensuring that specific attributes uniquely identify each row. This prevents duplicate records, like two entries sharing the same roll number, and facilitates efficient searching. The entity integrity constraint, the unbreakable anchor, mandates that the primary key of a relation cannot be null. Every record must have an identity, preventing unidentifiable records that would break retrieval and relationships. Referential integrity, the relational bridge, requires that a foreign key value must either match an existing primary key value in the parent table or be null. This prevents orphan records, such as an enrollment existing for a non-existent student. The domain constraint acts as the gatekeeper filter, specifying the permissible set of values a specific attribute can hold. The database management system blocks inputs that violate data type or hard limits, ensuring data remains logically possible. Value validation includes the check constraint, allowing custom logical validation rules, such as salary limits. The default constraint reduces data entry effort by automatically assigning a baseline value when no input is provided. Value validation also covers completeness and distinctness. The not null constraint guarantees data completeness by forbidding empty values in critical columns. The unique constraint eliminates duplicates at the column level, ensuring data distinctness. In a banking database, integrity constraints are vital. Entity integrity ensures customer_ID is not NUL. Unique constraint prevents duplicate customer IDs. Referential integrity links accounts to existing customers. Finally, the check constraint ensures the balance is never negative. The constraint diagnostic matrix summarizes the primary function, operational scope, and anomaly prevented by each constraint type. This matrix is a useful tool for understanding how each constraint contributes to data integrity. The value of an ironclad architecture is significant. Constraints prevent errors, facilitate efficient performance, provide security against illogical inputs, and ensure reliability by basing decisions on flawless data. Ultimately, constraints build trust in the system.